Is it not right because it is inefficient, it is a stupid thing to do, or is it not right because it is wrong? Yep.
For a computer, it would actually be more efficient. For us humans, it wouldn't be efficient because we already know that it isn't. We can use heuristics for
Correct. Yeah, but we still have not answered my earlier question. Is it wrong because it is inefficient? It is just an extra step that is not going to help me, or is it not right because it is wrong, as it will give me wrong results? It is just inefficient. Very good. Because any number that has a remainder of non-zero when I divide it by 2 will also have a non-zero remainder when it is divided by 4. In other words, there's no chance that I can misclassify 4 as a factor of this number. And as long as that is true, I'm just wasting time. Okay? I will not get a wrong result because of doing this. I will just be burning up processing time that otherwise I should not be burning. Okay? But this will greatly simplify the algorithm because I'm just testing numbers sequentially rather than using tricks to skip over certain numbers. Are we okay so far with this concept? Okay. So I would just use this approach here, okay? And frankly, I have no idea what is the next prime factor, but I know 5 is not going to be a prime factor, and I know 6 is not going to be a prime factor, and I will keep trying this until what?
You find one.
Okay, so we keep going like this until we say 2, 8, 3, 7, 8, 2, 8, 3 divided by a certain number. I would just call it f here. The quotient I throw away anyway, but this time I have a remainder of 0. Having a remainder of 0 means this number, or f in this case, is a prime factor of this number. Yep.
It's actually prime.
Hmm?
The number is prime.
The number itself is prime? How do you know? Oh, do you have a program to test it?
I can say factor it. I'll also say it's prime.
Wow, okay. What are the chances I pick a prime number of this magnitude? I mean, because you guys know that the distribution of prime numbers is going to get sparse and more sparse and more sparse as the number increases, because there'll be more factors or more multiples of something, as the number increases. So the chances of picking a prime number this big is actually pretty slim. In fact, they have an entire branch of mathematics/computer science dedicated to the search of huge, big prime numbers.
Why is that?
Very good question. Why do we care about prime numbers? Because it seems like prime numbers are just interesting things, but other than that, hey, what do we need it for? Go ahead.
Code breaking.
Code breaking. Now, how does prime numbers have anything to do with code breaking?
Because all code is math. If you can't use any division operations on something, that can cause some issues.
The key pair encryption, the AES, almost all of the ciphers or the encoding mechanisms that we use today, they're all based on prime numbers, big prime numbers. In other words, if you can search for huge big prime numbers, really, really quickly, you can actually, break code a lot, faster than without the ability to find prime numbers. Key pair encryption uses prime numbers, properties of large prime numbers. Do you guys know what is key pair encryption? Sort of? Okay. This is a slight digression. I would promise I won't be taking too much time to explain this, but it is something related to computer science, and that's one of the reasons why people are searching for these big prime numbers.
Those.
Okay, key pair encryption. I got two keys. Okay, so we'll just take a look at the key portion and not the fobs. So I got 2 keys here. In a normal sense, when you use a key, whatever key you use to lock up something is the same key that you use to unlock that something. But that's not good, because if you lose this one key or somebody has a copy of this key, guess what? That person can also unlock whatever you locked up. Key pair encryption is the interesting concept. Whatever key, so keys only come in pairs. Okay? So, we have one pair of keys like this. If I lock up something using this key, I cannot unlock it using the same key. If I lock it up using this key, I have to unlock using the other key. If I lock it up using this key, I have to unlock it using, once again, the other key. In other words, the terminology is actually symmetric. Okay? Now, I can designate one as private key. I can just randomly pick one and say, this is my private key. So my Honda key is my private key, my Toyota key is my public key. Okay? Now, the nice part about that is, now I can make sure I don't lose my private key. As the name implies, this one has to be kept private. So I lock up my car using my Honda key. And now, anyone with my public key can unlock my car. But none of them can lock up my car. Excuse me. They can all unlock my car. So what is the purpose of doing that? But at the same time, if I look into this as in a networking sense, what I can do is now I tell everybody about my public key. And I say, if you guys have anything sensitive to send to me and you don't want anybody else to know what you're sending to me, make sure you lock up your email messages using my public key before you send it. Okay? Now, what happens? The encrypted message that you send to me using the public key to encrypt it, it will go through all the email servers, different hops on the internet, and people can look into this message that is encrypted. And everybody has my public key, but can anyone else look at the content because it is locked by the public key?
No.
No, because the public key cannot unlock anything that it locks up to begin with. Okay, so everybody has a public key, but they cannot see the content already encrypted by the same public key. By the time it gets to me, then I pull out my private key, and then I can unlock the content. Okay, so that's the beauty of the asymmetric, method of using one key to lock and the other key to unlock, because the public key is no secret anymore. Okay, I can put it on my website and say, if you have anything sensitive to send me, lock it with this key. I can announce it to the world, and yet I have no, worry that people will be able to see what people are sending to me, because I'm the only one with a private key to unlock the content. Are you guys getting the basic idea of key pair encryption? And it also applies to DRM. Some people really hate that aspect of DRM, or digital rights management. How is it related to DRM? It can make sure that content can only be played on a certain computer. Because what happens is, this key is not even accessible to you as the owner of your own computer. Because it is on silicon. This is a part of the processor that you don't have access to. Okay? This one is sent to Amazon.com or iTunes or whatever. So the other side, using your public key, can encrypt a stream of audio stuff, video stuff, or whatever content, and make sure that the content is now encrypted. When it is stored on your computer and you try to play the content, there's no problem, because your processor does have the private key to unlock the content that is locked up by the public key. What happens when you try to play exactly the same file on a different computer? It cannot play anymore. Because the other computer, guess what? Is missing your private key. Okay, so that's how they can make sure that content can only be played on a particular computer or on a particular device, and it will not be of any use on other devices. Okay? Yep.
Is that in effect now? Is that
Oh yeah. Yes. Very much so. If you look into, I would suspect the same technology will be in all the ebook readers. Because this way you can basically make copies of all the files of an ebook reader, and if the content of a book is copy protected like this, you can copy that file to anything, and you would not be able to read the content because you don't have the private key on the other device to unlock the content.
That's why you can't take Office products from one computer to another.
Well, that's a different thing, but similar.
Without taking another program with it.
Yeah, you have to do certain things to make that happen. But anyway, that's the reason why prime numbers are so important. Because if you can crack prime numbers or figure out whether a large number is prime or not, and know its prime factors, you would have a huge advantage in terms of deciphering content, because you can try the possible keys a lot faster that way. Anyway, this is why we can exit, because the remainder is 0. So in this case, the number has to be itself when, in this case, f does equal to 28378283. Okay, because this number is prime. Okay. Good. So we now have a fairly good idea of the procedure to find a prime factor of a number. Okay, we start with 2. We divide the number by 2. If it does not work out, if the remainder is non-zero, we move on to 3. If the result is non-zero, we move on to 4. We keep doing this until we find a number such that it is a factor of the number that we are dealing with. Okay. So in this case, how many times do we have to do the division? Well, note what I asked. How many times do we have to do it? Now, in this case, using the more straightforward method, we have to do it about, 28 million times or so, okay? Even if you throw in all the tricks of using only prime numbers and whatnot, there's still a large number. But later on, I'll describe a trick where we only have to test up to the square root of this number. And then I can confirm it is a prime number. Now, the square root of this number is approximately what? Well, I can see a calculator, It's probably in thousands, okay? It's not even in tens of thousands. It's probably in some thousands.
5,327.
Okay, roughly 5,000 something. So instead of testing 20-something million numbers, I can test about 5,000 numbers, and then I can conclude the number is prime. Okay, so we'll talk about that little trick later on, but for now we'll go for the more simplistic way because we want to just get something up and running first. Okay, so the next thing I want to do, well, since I'm using an HTML editor, I can use the horizontal bar. Nice. Okay, so just like before, we come up with version 1 of the code. Do you think this thing is repetitive in some way, that we have to use a loop of some kind? Yeah. Okay, so we'll just say there's a loop involved. I don't know the content of the loop. I do not whether this is a pre-checking or post-checking loop. I just know that a loop is involved. That's all I'm saying. But whenever I have a loop involved, I want to say, do we exit this loop at some point? Is this supposed to be an infinite loop? No, it's not supposed to be an infinite loop. At some point, we should exit. When do we exit? When we have found a prime factor. Okay, not n equals 1. In this case, we are not factoring the number itself. We are just finding a single prime factor. Okay, so we'll just say when we have found a prime factor. Okay, very good. I called it my first version. Now you can see that the first version of this program really does not say much. Well, or does it? It actually does say something already, because it tells me when I'm supposed to get out of the loop. Okay, now how is that going to help me? Well, let's go for version 2, and in version 2, all I'm going to do is to introduce variables. Instead of saying this number, that number, and whatnot, we'll just say that, call the number in question n. In other words, we're trying to find a prime factor of n to be consistent with our earlier algorithm. Call a potential factor f, okay, which is also consistent with the terms that we used a little bit earlier. Okay, so just by using these two variable names, can I rewrite the loops so that it is more concise? When I have to say we have found a prime factor, what is the other way to express this now that we know something about f